Intervals and extrema. A function f is increasing on an interval if for any 2 points in the interval, a positive change in the x results in a positive change in the f of x. In other words, the graph is going up. Okay, when we say a positive change in the x, that means that we're going to the right. As we move to the right in the graph, do we get a positive change in the f of x? Does the output go up? If it does, we have an increasing graph. As we move to the right, the graph is moving up. That would be increasing. A function f is decreasing on an interval if for any 2 points in the interval, a positive change in the x. As you move to the right, if a positive change in the x results in a negative change in the f of x. So as you move to the right, does the output decrease? Does the graph go down? If so, then it's decreasing. A function can also be constant. It can be constant on an interval if for any 2 points in the interval, a positive change in the x results in 0 change in the f of x, 0 change in the output. If as we move to the right, we don't increase or decrease at all, we have 0 change, the function is constant. It is a flat line. It is a horizontal line. Example 1. For each function, let's identify the intervals for which the graph would be increasing or decreasing. For f of x, x plus 2 to the second power, we're going to get a graph of a parabola with a vertex at -2. All right, so let's go ahead and take a look at this. I've already got it typed in. We'll go ahead and graph it. We get a parabola. It's a quadratic function. We get a parabola with a vertex at -2. Okay, now from the left, all the way to the left, up until you get to that vertex, the graph is decreasing. As we move to the right, the outputs are getting lower and lower until they get to that vertex point. At that point, which would be -2, where x is -2, the graph begins to increase. Okay, so for our intervals, we're going to be decreasing, I'll just call that d, we're going to be decreasing from -infinity up until -2. And I am going to use parentheses around the -2 because at that point it isn't increasing or decreasing. It's actually a transition point between those two. It then increases from -2 to infinity. The graph of g of x is going to be a little bit more interesting than the graph of f of x. We do have x in the denominator, and you may recall that that can cause us to get either holes or asymptotes with these graphs. So we're going to type it into the calculator, we're going to take a look at the graph, and then we're going to use that to identify the increasing and decreasing intervals. All right, so let's take a look at the graph. You're going to see that it looks like we have a horizontal asymptote. Okay, in addition to that, you've got a couple of vertical asymptotes. Ultimately, it breaks it into 3 sections. The graph has 3 parts. The first, over here to the left, is going to be an increasing interval. It doesn't increase by much down here by that horizontal asymptote, but it is increasing and then at some point just sort of takes off. All right, the next section of the graph is a lot like that parabola where it's got 2 parts. It has an increasing part up until it gets to the origin, then it turns back down to decreasing. The third part is a decreasing interval. It starts high, then it decreases towards that horizontal asymptote. Okay, so we actually have 4 intervals. We've got 3 parts to the graph, but if we're talking about increasing and decreasing intervals, we actually have 4 parts. Okay, decreasing, we've got -infinity up until we get to that asymptote, up until we get to there. And these vertical asymptotes, we can figure out what they are by actually factoring the denominator. This is the difference of squares, which is going to factor into x plus 1 times x minus 1. That means that those vertical asymptotes are at -1 and +1. Okay. All right, so I stated this as decreasing. It's actually increasing. Incorrect there. We're increasing from -infinity up until we get to -1, which that will be parentheses. Okay, it doesn't actually increase at -1. That's an asymptote. The graph will also be increasing for the first part of that, which is going to pick up again at -1. and go to 0, parentheses at 0, it's a transition point. The graph is then decreasing from 0 to 1 and decreasing again from 1 to infinity. We've got increasing, we've got increasing, we've got decreasing, we've got decreasing. Many graphs are characterized by peaks and valleys. These would be the high points and the low points of the graph. So if we're physically describing what a graph looks like, we tend to gravitate towards those areas. We talk about high points and low points. These points are going to be important because they're the transitions between increasing and decreasing intervals. Okay, these transitions are also called extrema. A peak is going to be a maximum, and a valley, a low point, is going to be a minimum. A local maximum of a function is going to be a value of f of c. That's an output. Is going to be a value of f of c that is greater than all the range values that would be the other outputs in an open interval that contains c. In other words, if you were to break off a section of a graph and look in just that section, if there is an output at a certain value of xc that is greater than all the other outputs, we can refer to that as a local maximum. It is the highest point within that area. Now, if f of c is greater than all the range values, all the outputs of f, then we refer to that as an absolute maximum. Okay, so a local maximum is the highest point in a certain area. The absolute maximum is going to be a highest point overall. The same thing can be said about minimums. You can have a local minimum, which is a lowest point in a certain area, but you can also have an absolute minimum, which is a lowest point of a graph. And it is possible that you don't have a local maximum or local minimum or an absolute maximum or absolute minimum. Think of just a basic line graph. That doesn't actually have a highest point or a lowest point. Okay, so this is a unique feature that you'll tend to see in functions that might be polynomials, such as quadratics. All right, example 2. This is a picture of the graph that goes with the function f of x. What we want to do is decide if it has any local maxima, local minima, or if it has anything that is absolute. So to do this, we basically look at any peaks or valleys, like this point here. Okay, we have a low point there. That would be a local minimum, okay? All right, so we have a local minimum, and you're gonna answer this with the output value that goes with it. So that appears, let's see if that's gonna be -10, that'd be -20. We're counting 1, 2, 3, 4, 5, -24. So it appears that it's at -24. Okay, we also have a peak right here, which that we might need to just estimate. Let's just say that that's at about a height of 1. So we have a local maximum at 1. Then over here, you also have another low point. Okay, not as low as what we've got there, but in that general area, we have a low point. So we have a local minimum that would also be at most likely -2. All right, so of this group of local maximums and minimums, is there anything that is absolute? Is there any point that is lower than every other point within the graph, or is there a point that's higher than any other point? And we have one. That first point here is an absolute minimum. This here is a high point, but if you look at the ends of the graph, this graph appears to continue on forever up. So it does not have an absolute maximum. It does have a local max at that point. And within this area, that appears to be the highest value. All right, some additional things to bring up here. A function f is bounded above if there's an absolute maximum. If there is a highest point that it never goes beyond, we can say that it's bounded above. If it has an absolute minimum, we can say that it is bounded below, which is our case here. This is a graph that is bounded below. It does not go below that value here. If your graph is both bounded above and below, we can simply say that it is bounded. So if you say it's bounded, that means it does have an absolute maximum and it has an absolute minimum. This graph, this function here, is bounded below, but not bounded above.
Wait, what?